The James Webb Space Telescope, moreover known as Webb or JWST, is a reliable pioneer that has uncovered amazing pieces of information concerning stars, planets, universes, and other intriguing boundless characteristics, as well as setting new principles for logical energy. Webb is hailed as the regarded Hubble Space Telescope substitution. People from one side of the planet to the other are trading photographs or utilizing raw data to make new discoveries. 3 minutes prior, James Webb caught the most ridiculously upsetting picture ever found in history. 1 year has passed since the amazing James Webb Space Telescope revealed its absolute first central picture of the universe, stunning stargazers across the world with its great detail. Yet its most recent finding is a bewildering picture of the universe that we have never seen before. What has been seen to this point by the James Webb Space Telescope is uncovering more leap forwards than it oversees. Researchers say the substitution to the Hubble scope uncovered new data about star development, universe blends, and the early universe. Only 1 month after the beginning, photographs were delivered. The photos were amazing, revealing the universe thoroughly. From that point forward, the number of divulgences has taken off, giving researchers a huge information mother lode. James Webb Space Telescope's pictures of grandiose tarantulas, record-breaking space smoke, stars, almost their huge impact influences, and other superb heavenly objects have been recorded. This satellite observatory's top-tier headways permit us to peer farther into space than previously, revealing beforehand dim subtleties about the universe. A portion of this is coordinated as a technique for reviewing the main year of the James Webb Space Telescope's action. NASA delivered a picture appearing a little star-forming district in the Rucci Cloud Complex. The picture shows planes shooting from child stars as enormous development floods of different assortments influence atomic hydrogen, which makes up the red development. The presence of a circumstellar circle makes a few theories about a barely few stars, proposing the chance of planet development in the far-off past. The picture could show great confusion, yet as per NASA, this radiant nursery is small and serene compared to others. The lively stars in this district are about the size of our Sun or even more modest, making it the closest star-forming locale to Earth. This image was caught by the essential camera of the observatory, the Webb Space Telescope's close infrared camera, which captures dazzling pictures in 2 particular infrared reaches at the same time. Furthermore, the Space Telescope has improved our comprehension of exoplanets, or planets that circle stars other than our Sun. James Webb is especially capable at contemplating far-off monstrous worlds. The satellite observatory found its first exoplanet, LHS 475b, toward the start of 2023. The planet is 41 light-years away and has a diameter like Earth's. James Webb, as indicated by NASA, is the only functional telescope prepared to do sequencing the air of Earth-sized exoplanets. The discoveries delineated how exact the telescope was. Harsh exoplanets are now another frontier for stargazers to investigate. The James Webb Telescope also tracked down proof of antiquated cosmic systems that, from a hypothetical point of view, shouldn't have existed. The Advancement Lab of Swindon School and its grandiose group have found 6 epic antiquated systems called universe breakers, which could substantially influence how we might interpret space. These giant universes could have showed up between 500 to 700 million years after the Big Bang. Authorities on the matter agree. Recently, the telescope's infrared sensors identified them, permitting us to think back in time around 13.5 billion years, when stars and cosmic systems were considerably more settled. The enormous size of the universe breakers has left researchers perplexed. Systems in the early universe ought to have been 10 to 100 times less than their ongoing size. These 6 items might be billions of times heavier than our Sun, and the overall mass of stars in a solitary world could be 100 billion times heavier than our Sun. Does attempting to fathom something so huge make you feel uncomfortable? In spite of mechanical progressions, planets that are incredibly huge to exist have specialists confounded. None more so than the discovery of a planet remembered to be excessively enormous for its star. This has prompted a reassessment of our whole comprehension of planet development and planetary system design. A planet that is commonly just about as extensive as Earth has been seen by research from Pin 8. Tales suggest that this planet is in a planetary system around the ultracool star LHS 3154, a star that is commonly more modest than our Sun. Before really seeing it for themselves, researchers didn't think such a circumstance was conceivable, Yet new proof shows that the largest planet in our planetary system is, in fact, circling one of the universe's littlest, coolest stars, a ultra-cool dwarf. We still have practically no comprehension of the universe. This discovery shows that a planet of this mass circling a star with such a low mass overcomes our presumption. These stars could have formed in tremendous gas and dust mists. Planets could arise from the gas and dust that remain in the circle of material around the infant star. Anyway, it isn't estimated that the planet-forming circles around the low-mass star LHS 3154 contain sufficient strong mass to create this planet. In any case, it exists, so we should now re-examine our speculations about heavenly and planetary development. A decent similarity is balance. A star with an outside heat source must keep up with its inner temperature. You need to draw nearer to the intensity source as its temperature diminishes. Planets are the very planets that ought to be warm enough to support fluid water and should be nearer to their stars. For instance, Earth is in the livable zone due to the warmth and light it gets from the Sun. The distances of different planets from our Sun are either excessively perfect or too little for them to get the right measure of light to support life. Now, envision a universe with a much cooler star. Drawing nearer to the fire would be comparable for planets circling a cold star to get the perfect proportion of energy to support life. The planet size ought to likewise be changed in accordance with give the best distance for energy and light to help life. Getting back to our past conversation, there are various theories for why the planet might have formed close to the little star. As per a generally held conviction, the planet could have been a lot bigger at first. Over the long run, the planet would have lost a lot of its mass. Anyway, this hypothesis has a significant blemish since huge mass causes a planet to lose a larger number of gases than solids. In this case, it is conjectured that the vast majority of the planet's mass would have been remains, which is conflicting with the finding. Another clarification is that this gigantic planet formed far from the little star. If the planet had the option to try not to get too much light, it would probably be ice-covered. The star could ultimately gravitationally draw in this far-off planet, bringing about this monstrous planet being near the little star. Despite the fact that both thoughts make sense of the noticed planet-star match, researchers are still incapable of completely comprehending the abnormality. With cutting-edge technologies like JWST, specialists are presently inspecting planetary frameworks more meticulously, and each new finding is pushing them forward. We have dove all the more profoundly into how the universe has shaped over the last months than we have over the most recent 30 years. The tremendous measure of information provided by the telescope has proactively prompted major logical advances that have astounded stargazers and sparked interest in future space investigation. With the James Webb Space Telescope in activity for a year now, one thing is sure: the universe is undeniably more complicated than we recently envisioned, and there are a large number of questions we presently can't seem to answer. The James Webb Space Telescope, JWST, sent off by NASA in December 2021, addresses a stupendous jump forward in our mission to figure out the universe. Named as the replacement to the Hubble Space Telescope, JWST is outfitted with trend-setting innovations intended to catch remarkable perspectives of the universe across a more extensive range than ever before. At the core of JWST's abilities is its enormous essential reflect, bragging a width of 6.5 meters, 21.3 feet. This size is over 2 times that of Hubble's mirror, permitting JWST to gather and shine altogether more light. This expanded light-assembling power empowers JWST to notice fainter and more far-off objects with excellent clearness and detail. One of JWST's key instruments is the near-infrared camera NIRCam, fundamental for noticing the universe in the infrared range. Infrared light is significant for concentrating on divine articles, since it infiltrates grandiose residue mists that block apparent light, uncovering stowed-away stars, systems, and planetary frameworks. NIRCam works in 2 infrared frequencies simultaneously, giving stargazers significant information on the temperatures, compositions, and developments of far-off divine bodies. Another critical instrument on board JWST is the near-infrared spectrograph, NIRSpec, which separates light from far-off objects into its part colors or spectra. By investigating these spectra, cosmologists can determine the synthetic composition, temperature, and movement of stars, worlds, and exoplanets across tremendous distances. This capacity is significant for concentrating on the development of stars and universes, the development of planetary frameworks, and the heirs of exoplanets. JWST's mid-infrared instrument, MIRI, supplements NIRCam and NIRSpec by zeroing in on much longer infrared frequencies, fundamental for considering the coolest objects in the universe. MIRI's high-level indicators and spectrographs empower itemized perceptions of cold gas mists, dust, covered star-forming districts, and the warm outflows from far-off planets. Along with NIRCam and NIRSpec, MIRI gives a complete perspective on the universe across an expansive scope of infrared frequencies. Quite possibly of the most expected capacity of JWST is its capacity to study exoplanets, planets circling stars beyond our planetary group. JWST's strong instruments permit stargazers to dissect the climates of exoplanets as they pass before their host stars, a strategy known as transit spectroscopy. By estimating the changes in starlight separated through an exoplanet's air, JWST can recognize gases like water vapor, carbon dioxide, and methane, providing bits of knowledge into the planet's atmosphere composition and likely livability. Notwithstanding its logical instruments, JWST's circle around the second Lagrange point, L2, roughly 1.5 million kilometers, 930,000 miles, from Earth, guarantees insignificant obstruction from Earth's environment and intensity. This stable vantage point permits JWST to keep a reliably cool temperature, fundamental for its infrared perceptions, and provides continuous perspectives on the universe for extended periods. The excursion to send off JWST has been many years in the making, with global collaboration among NASA, the European Space Organization, ESA, and the Canadian Space Agency, CSA. Each organization contributed special skill and innovation to the telescope's improvement, guaranteeing its prosperity as a worldwide undertaking in space investigation. Logically, JWST aims to address essential inquiries regarding the universe's beginnings, development, and composition by noticing the universe in infrared light. JWST can look through vast residue mists, concentrate on the development of stars and universes, and investigate the conditions fundamental for planets to shape and support life. These perceptions will expand upon the revelations of past telescopes like Hubble and change how we might interpret the universe. One of JWST's essential logical objectives is to concentrate on the main stars and universes that framed in the early universe. By identifying the weak infrared light produced by these antiquated objects, JWST can test further into grandiose history than any time in recent memory, disentangling the secrets of how the universe progressed from a hot, thick state to one loaded up with stars, systems, and ultimately planets. One more key area of investigation for JWST is the examination of star development and planetary frameworks inside our own Milky Way universe. JWST's high-resolution imaging abilities permit stargazers to notice protostars, the forerunners to stars, inserted inside thick gas mists. These perceptions give experiences into the cycles that drive star arrangement and the development of planetary frameworks around youthful stars. Besides, JWST's perceptions of planetary frameworks past our solar system offer a brief look into the variety of exoplanets and their potential for tenability. By contemplating the climates of exoplanets, JWST can recognize synthetic marks that may show the presence of life-supporting conditions, like fluid water or organic molecules. These disclosures will illuminate future investigations and missions aimed at finding Earth-like planets capable of supporting life. Past its logical targets, JWST represents a mechanical wonder in space engineering and instrumentation. The telescope's complicated arrangement sequence, which incorporates unfurling its divided reflect and sunshield, required exact engineering and testing to guarantee fruitful activity in space. JWST's instruments went through thorough testing to endure the brutal states of space, including outrageous temperatures, vacuum conditions, and radiation openness. The advancement of JWST, moreover, pushed the limits of worldwide cooperation in space investigation. Researchers and engineers from around the world added to the telescope's plan, development, and testing, utilizing expertise in optics, material science, aviation design, and astronomy. This cooperative exertion ensured that JWST would accomplish its logical objectives and make way for future space missions. Looking forward, JWST vows to alter our comprehension of the universe and rouse future generations of cosmologists, researchers, and space voyagers. The telescope's uncommon capacities will empower revelations that were once thought unthinkable, from disentangling the secrets of dull matter and dull energy to contemplating the airs of far-off exoplanets. Additionally, JWST's revelations will have significant ramifications for our comprehension of Earth's position in the universe and our true capacity for life beyond our nearby planetary group. By examining planetary frameworks and their development, JWST will provide bits of insight into the conditions fundamental for livability and the variables that shape planetary conditions over vast periods. In conclusion, the James Webb Space Telescope remains at the forefront of 21st century stargazing, ready to reconfigure our comprehension of the universe. With its advanced instruments, global cooperation, and ambitious logical objectives, JWST represents a demonstration of human resourcefulness and interest in the universe. As JWST begins its journey of investigation, it holds the promise of disclosing new discoveries, replying central inquiries regarding our origins and existence, and inspiring future ages to explore the wonders of the universe.